Hello, in this video we're going to be looking at how to model with differential equations, having looked at how to solve differential equations in a previous video. We're going to be looking at three scenarios: population growth, radioactive decay, and the cooling curve. So for scenario 1, population growth, the graph shows the exponential growth of a badger population starting with 150 badgers and increasing at a rate proportional to the current population. So if we look at the graph, just ignore the bit to the left of 0. It starts at 150 on the y-axis or the population axis, and it is growing exponentially as we go from left to right. And we can write that as dp by dt, which is the rate of change of growth, is equal to kb, because it says it's increasing at a rate proportional to the current population. Now the amazing thing is, just based on the information we've got there, we can come up with a formula for P. So dP by dt equals Kp. So just as we saw in the previous video on solving differential equations, we can get all the P's on the left, all the T's on the right. So divide by P and times by dt and integrate, and we get the integral of 1 over P dP is equal to K times the integral of dt. So the left hand side is ln P, and the right hand side, the integral of K, or 1, with respect to t, we end up with kt plus a constant c. Now we can work out the value of c. We can't work out the value of k, we need more information for that. But we can work out the value of c because we're told that it starts with 150 badgers. So that means that when t is equal to 0, p is equal to 150. Substituting those numbers into ln p equals kt plus c, we get ln 150 equals nothing plus c. So c is ln 150. Substitute that into our ln p formula. We get ln p equals kt plus ln 150. If we move the logarithms all to the same side, we get ln p minus ln 150. And then we can use the rule of logs that says subtraction is division. So ln of p over 150 equals kt. If we then exponentiate both sides, we get p over 150 equals e to the kt, from which p equals 150 e to the kt. Having got our expression for p equals 150 e to the kt, we may then be asked to work some other things out. So in the first part of this question, it says given that k equals 0.045 and t is in years, find the population of badgers after 15 years. Okay, so all we have to do to work that out, there's no calculus involved. We substitute 0.045 for k. So we have p equals 150 e to the 0.045 t, and then we substitute in 15, and that gives us 150 e to the 0.045 times 15, which equals 294.6. So we round that to 295 because we want a whole number of badgers. And as well as working out p for a value of t, we can work out t for a value of p. So if p equals 150 e to the 0.045 t, and we're told that p is 220, we can substitute 220 for p and then solve the equation. To do that, we divide by 150. That gives us e to the 0.045t equals 220 over 150. We then take logs of both sides, so 0.045t is equal to log of 220 over 150. Divide by 0.045 and we get an answer of 8.51 years. Now we're going to look at an example of radioactive decay. So the graph shows the exponential decay of the activity of a radioactive substance, starting with an activity of 3.00 times 10 to the 14 becquerels and decreasing at a rate proportional to the current activity. So again, we've got an initial value of, in this case, 3 times 10 to the 14, and we ignore everything to the left of my graph, left of the y-axis. This time it's exponential decay, and that's why the formula has a minus sign in it to show that the gradient is negative. So dA by dt equals minus Ka, and we start in the same way. We're going to divide by a and times by dt, so we get the integral of 1 over a dA equals minus Ka times the integral of dt, from which ln a equals minus kt plus c. And then again, we've got an initial condition. When t equals 0, a is 3 times 10 to the 14. When we substitute those numbers in, we get ln of 3 times 10 to the 14 equals nothing plus c. So we have C as ln of 3 times 10 to the 14. Substitute that back into the formula, take it away, divide, and we get ln of A over 3 times 10 to the 14 is equal to minus kt. Exponentiate both sides, times by 3 times 10 to the 14, and we get A equals 3 times 10 to the 14 times e to the minus kt. And then the second part of the question. After 100 days, the activity is 2.18 times 10 to the 14 becquerels. Find the number of days that have passed until the activity is 8.3 times 10 to the 13 becquerels. Now, at this point in the Badger question, we were told the value of K. In this question, we have to work it out using the information. So when T is 100, A is 2.18 times 10 to the 14. So we substitute for A equals 3 times 10 to the 14 e to the minus kt, where T is 100. So that's e to the minus 100k. We can divide both sides by 3 times 10 to the 14. So we get 2.18 over 3 is equal to e to the minus 100k. Log both sides, divide by negative 100, and that gives us k is equal to 0.00319 to 3 significant figures. So now we have a value for k. We can work out the number of days that have passed until the activity is 8.3 times 10 to the 13 becquerels. So we've got a new activity of 8.3 times 10 to the 13 equal to our initial 3 times 10 to the 14 times e to the minus kt, where k is 0.00319. We can divide both sides by 3 times 10 to the 14, which gives us 83 over 300. Take logs of both sides, divide by k or negative k, and that gives us t as 402.8 or 403 to the nearest whole number. In scenario 3, we have a cooling curve. The graph shows the exponential cooling of a mug of coffee starting at 94 degrees Celsius and decreasing at a rate proportional to the current temperature above room temperature, 21 degrees Celsius. So with radioactive decay, for example, things would decay until they became zero. But with cooling, it's only going to decay or cool down until it gets to room temperature. It's not going to suddenly turn into a block of ice when it's left in a room. So that's why we have a slightly different looking equation. d theta by dt is equal to minus k times theta minus 21. Okay, so that means that theta will always be bigger than 21. Now we can solve this in a similar way, but rather than having minus ka or kp as we had earlier, we've got minus k times theta minus 21. So we're going to divide by theta minus 21 and times by dt. So that gives us the integral of 1 over theta minus 21 d theta is equal to minus k times the integral of dt. And then if we wish, we can integrate by substitution to get ln of theta minus 21 equals minus kt plus c. So the initial temperature of the coffee was 94 degrees, so theta is 94, so and t is 0, so that gives us ln of 73 is equal to 0 plus c, so c is log 73, and then substitute that in, we get log of 0 minus 21 equals minus kt plus log of 73. And I'm sure you'll have noticed that throughout these videos I've said ln or ln or log, and they mean the same thing every time. So we've got log of theta minus 21 equals minus kt plus log 73, and I'm still looking for a formula for theta. So I can take away log 73 from both sides. I can use the rule of logs that says subtraction is division. So log of theta minus 21 over 73 is equal to minus kt. I can exponentiate both sides, which gives me theta minus 21 over 73 equals e to the minus kt. I can times by 73 and add 21. And so my formula for theta is theta equals 21 plus 73 e to the minus kt. And then to complete our final scenario, we've been asked 3 questions. Explain why theta cannot fall to 10 degrees Celsius. The temperature of the coffee after 15 minutes is 40.8 degrees Celsius. Find the temperature of the coffee after 20 minutes. And finally, find the time at which the temperature of the coffee is 58 degrees Celsius. So explain why theta cannot fall to 10 degrees Celsius. Well, we already know for physical reasons and from the graph that it's impossible for the temperature of the coffee to go below room temperature. But if we also look at the equation, theta equals 21 plus 73 e to the minus kt, if we were to substitute theta as 10, then e to the minus kt would equal 10 minus 21 over 73, which would be a negative number, and e to the x cannot be negative, and hence theta cannot get to 10. So for the second part, the temperature of the coffee after 15 minutes is 40.8 degrees Celsius, while the temperature after 20 minutes. I'm going to spend most of this part of the question working out the value of K. So theta equals 21 plus 73 e to the minus kt. Substitute 15 for t, substitute 40.8 for theta, and that gives us 40.8 equals 21 plus 73 e to the minus k times 15. We can simplify that a bit by taking away the 21. We can divide by 73. We can take logs of both sides and divide by negative 15, and we get k as 0.087 to two significant figures. And then if we substitute that back into the original equation, theta equals 21 plus 73 e to the minus 0.087 times t. And then if we substitute t as 20, we get an answer of 33.8 degrees Celsius. And then to find the time at which the temperature of the coffee is 58 degrees Celsius, we now know what K is. So theta is 58, that equals 21 plus 73 e to the minus kt, where K is 0.087 to two significant figures. Take away the 21, divide by 73, take logs of both sides, divide by minus 0.087, and that gives us an answer of 7.8. And because time is in minutes, it's 7.8 minutes.